Hello, math humans. We're going to do 2.2a today. We're going to be talking about graphs of polynomials. Our objectives are that we're going to talk about the characteristics of polynomial graphs. We're going to look at end behavior, the leading coefficient test, and then zeros of a polynomial. For starters, the graphs of a polynomial are continuous. So that means that I have to have one continuous graph. There can be no breaks. There can also be no sharp points. So the absolute value graph is actually not a polynomial. Alrighty, so we tend to think of power functions when we think of a polynomial, and that would be something that's y is equal to x raised to a power. Alrighty, some cool things about n. If n is even, then the graph is going to kiss or bounce off of the x-axis, so we're going to call it a bounce. And then if n is odd, then the curve is going to go through the x-axis. So this would be if n is odd, and this would be if n is even. So this is going to be a through the axis. Alrighty, so that sometimes helps us to know what a graph of a polynomial looks like, even if I don't happen to have my grapher handy. Alright, the next topic that we want to talk about, it looks like my orange pen is unhappy, is end behavior. Let's see if I have another one that will work better. Oh, look at that. So for the end behavior, we're looking at what happens at the extreme ends of the function. And then we have some very specific notation that we use when we're talking about end behavior. So for example 1, that's an x. So for example 1, we're just going to look at a cute little parabola. So if we look at the function, I want to look at what happens as I approach negative infinity and what happens as I approach positive infinity. So when we're talking about end behavior, the notation would be as x approaches a negative infinity. So that is x goes to the left forever. Then I talk about the y values are going to approach positive infinity. And that means that the y values are just going to go up forever. And as x approaches positive infinity, the y values are also going to go up. Okay? All right, so it's actually not very hard, but it helps us, again, to have a picture of what a graph looks like at its extreme ends. All right, so here's the second example. So I'm going to have a crazy-looking function. So it's just going to do some crazy stuff, and it might look like that. Well, if I want to talk about the end behavior, as x approaches a negative infinity, the y values are approaching negative infinity. As x goes to the left forever, the y's are going down. And as x approaches positive infinity, the y values are also approaching positive infinity. As you move up in math courses, you don't always have access to a calculator, and so sometimes we need to be able to come up with what does a graph potentially look like, even if I don't have access to a calculator. All right, we're going to look at one more function, and it might be something that's raised to the fourth power, because oftentimes a fourth degree polynomial looks kind of like a W. So if I'm talking about the end behavior, and on an exam or a quest, I don't mind if you write EB because we would understand that that means end behavior. As x approaches a negative infinity, the y values are approaching positive infinity. As x goes to the left, y is going up, and as x approaches positive infinity, y is also approaching positive infinity. Now, if you'll notice, I started with the left-hand side of the graph. Because we do math left to right, I typically start reporting and start with my left-hand values. All right, the next thing that we want to talk about is the leading coefficient test. All right, and again, it's just another way of looking at a graph in case I didn't have access to a calculator. So if I had y is equal to ax to the third plus bx squared plus cx plus d, or any other flavor of polynomial, a is always going to be the leading coefficient. If a is positive, then the function behaves like the parent function. And if a is negative, then f behaves as a reflection. And remember, it would specifically be a reflection across the x-axis. All right? So things that we know, we can also talk about for my leading coefficient. We can also talk about the power for the leading term. So if n is even, we talked that that would be a bounce, right? It also means that it affects the end behavior. So the end behavior is going to behave like the parent function. And if n is odd, then it's going to be a through and through, right? So the function is going to go through the axis, and then the end behavior is also going to behave like the parent function. So the only thing that changes the direction of the graph is if A, the leading coefficient, is negative. All right, the next topic that we want to talk about are zeros. I think that E is not supposed to be there. I always can't decide if it is or if it isn't. So if we want to talk about the zeros of a function, that's everywhere that it crosses the x-axis. So those are the x-axis. When we're talking about an intercept, remember that we have to report as x and y. But for the zeros of a function, I can report as x is a number and another number, right? So it's actually, I think, much nicer if they ask you to find the zeros, because then I don't have to write my solutions in ordered pair notation. All right, the next concept is turning points. So we're looking for all of these different clues that can help us know what a graph is going to look like in the event that I don't have access to a grapher. Turning points are the point, or points, I'm going to put it in parentheses, where a function's slope changes from positive to negative or negative to positive. Okay, so for example, let's say I have a curve, let me scoot my paper up, that does something like this. So in theory, this would be a 1, 2, 3 degree, so this is a third degree polynomial. That means that the n is 3. So then the number of turning points is n minus 1, which is going to be 2. And if you'll notice, this is a positive slope, this is a negative slope, so this is a turning point. And then I have a negative slope to a positive slope, that is the second turning point. So turning points are always the degree of the equation minus 1. All right, the next concept that we have for this particular section is multiplicity. And this means that there are repeated zeros. So if n is even, that means that I would have a bounce. And then it also potentially means that I have an even multiplicity. If n is odd, remember that means that the function goes through the x-axis, and there probably is going to be an odd multiplicity. All right, so the easiest way to talk about multiplicity is, let's say I have a function written in factored form, and it looks like this is to the first power, x plus 3 to the second power, and x minus 5 to the fifth power. This would be a 5, 6, 7, 8 degree, so that means the highest power would be an 8, and it also means that this particular 0, x is 2, would have a multiplicity, and I'm just going to write multiplicity of 1, because the power determines the multiplicity. This is x is equal to a negative 3. It has a multiplicity of 2, and I get a little bit lazy when I'm writing it down, and I just write m2. And then this 0 is x is equal to 5 with a multiplicity of 5. And again, these are just characteristics of the graph that will help you note what the function potentially looks like. All right, we're going to do the fourth example now, and it says find all, which is a key word. We'll have more about that in the next sections, zeros, and then determine multiplicity. All right, the function is going to be f of x is equal to a negative 2x to the fourth plus 2x squared. We're going to start the problem by factoring, because factoring is your favorite F word. So I'm going to take out a negative 2. They both have an x squared in common, and I'm going to get x squared minus 1. This piece then factors to be x plus 1 and x minus 1, because it is a difference of 2 squares. So then my zeros, x is going to equal 0 with a multiplicity of 2, and that is coming from this one. So if I set that particular piece of the factoring equal to 0 and solve, I would get x is equal to 0. The degree determines the multiplicity. And then from these two factors, I would get plus or minus 1. So this was a fourth degree polynomial, and I have 1, 2, 3, 4 zeros. Right? The multiplicity I wrote down as I went along. Typically, if a factor has a power of 1, we do not report the multiplicity. All right, let's do another example. This is example 5. It says, find all zeros, and then determine, forgot the I, the multiplicity. I'm just going to write it that way. And then determine the turning points. All right, the function is going to be g of x is equal to x plus 2 quantity squared, 3x minus 5 to the third, and x plus 1. So because they gave it to you in factor form, it actually is really pretty simple. X is going to equal a negative 2 with a multiplicity of 2. X is going to equal 5 thirds with a multiplicity of 3, and then x is going to equal a negative 1. Technically, it has a multiplicity of 1, but we often don't report it when it has a multiplicity of 1. Okay? This would be a bounce, this would be a through, and this would also be a through. So that gives you more hints about the graph. Now remember that the turning points are n minus 1. The degree of this is 2, 5, 6. It's a sixth degree polynomial. We take away 1, so it's 5. So there are potentially 5 turning points. All right, I think we only have one more example. So let's do that one, and then we're done for today. All right, this one says, find a polynomial in standard form. Remember that there are multiple forms for a polynomial, and we always want to make sure that we read our directions well. Given the zeros, x is equal to 2, 4, and a negative 1, and they're going to tell us that it's a third degree polynomial, which means that each of the zeros, since there are 3 zeros, has a power of 1. So the way that we start is we write it in factored form, because that's easiest. So it's always going to be x minus the factor, right? So if I start, it's going to be x minus 2. x minus 4, and x minus a minus, so x plus 1. And this would be my function, but remember, this is in factored form, so now we have to do some more work. So I'm going to distribute those two guys, and I'm going to show it to you. Actually, we can do this one pretty easy without doing more work. So this is x squared minus 6x plus 8, and then that's going to be multiplied by x plus 1. So now I tend to do these in a box, and I'll show you how I do them because I like the way it organizes the information, and then I don't have to think as hard. So notice I took this factor and I wrote it over here. This is going to be these at the top. Each cell comes from the product of these two things. So this is x to the third, x squared, minus 6x squared, minus 6x, 8x, and then 8. And notice that your like terms are along the diagonal, so it organizes your information really politely. So then if I just combine like terms, this is x to the third, and negative 6 and a positive 1 is minus 5x squared. 8x minus 6x is plus 2x plus 8. And then we report well, and we just rewrite it and identify it, because if you forget to identify it, you lose points. Sad day. Alrighty, that is it for today. I will see you soon.